the structure so large it broke our understanding of space. That is not an exaggeration. That is not clickbait. That is the simple truth of what astronomers discovered when they pointed their telescopes toward a patch of sky that seemed ordinary at first glance. What they found there changed everything we thought we knew about how the universe works. It challenged the very laws of physics that had guided our understanding for over a century, and it made us realize just how small we truly are in the grand scheme of existence. Imagine standing on a beach, looking out at the ocean. You see waves rolling in, stretching from one end of the horizon to the other. Now imagine discovering that what you thought was the entire ocean is actually just a single drop of water in a bathtub, the size of a continent. That is roughly what happened when we found this structure. Everything we thought was big suddenly became almost meaninglessly tiny. If you enjoy these journeys through the cosmos, consider subscribing and leaving a like. It helps this channel grow and allows us to keep exploring the strangest mysteries of our universe together. But here is what makes this discovery truly unsettling. According to our best theories of how the universe formed and evolved, this structure should not exist. It is too big. It is too old. It defies the fundamental limits that physics places on how large anything can possibly get. And yet there it is, stretching across the void, like some impossible monument built by forces we do not understand. Some scientists have called it a crack in our understanding of reality. Others have suggested it might be evidence that our entire model of the cosmos needs to be rewritten from scratch. So what exactly did we find out there in the darkness between galaxies? How big is it really? And what does its existence mean for our understanding of where we came from and where the universe itself is heading? To answer these questions, we need to start at the very beginning. We need to understand what the universe looks like at its larger scales, and why finding something this massive should have been impossible. Let us begin our journey by zooming out, way, way out, past Earth, past our solar system, past the nearest stars. Keep going until our entire Milky Way galaxy becomes just a smudge of light, a spiral of 400 billion stars reduced to something you could cover with your thumbnail. Now keep going further. Past our neighboring galaxies, past the local group, past clusters of thousands of galaxies bound together by gravity. At these scales, something remarkable happens. The universe stops looking random. A pattern emerges. Galaxies are not scattered evenly throughout space like dust thrown into the wind. Instead, they clustered together along vast strands and filaments, like dewdrops clinging to the threads of a cosmic spider web. Between these strands lie enormous voids, regions of almost complete emptiness stretching for hundreds of millions of light years. This grand pattern is called the cosmic web, and it is the largest structure in the known universe. Or at least, that is what we thought. The cosmic web is not something we invented or imagined. It is something we discovered through decades of careful observation and mapping. Astronomers have catalogued millions of galaxies, measuring their positions and distances, slowly building up a three-dimensional map of the universe around us. And what that map revealed was breathtaking. The universe has architecture. It has structure at scale so vast that light itself takes billions of years to cross from one side to the other. Think about that for a moment. Light travels at 186,000 miles per second. In 1 year, light travels almost 6 trillion miles. We call that distance a light year. Our nearest neighboring star system is about 4 light years away. Our galaxy is about 100,000 light years across. The filaments of the cosmic web can stretch for hundreds of millions of light years. These are distances so large that our brains simply cannot comprehend them in any meaningful way. But here is the crucial point. The cosmic web, as impossibly vast as it is, follows rules. It obeys the laws of physics. It formed through a process we understand, at least in broad strokes. After the Big Bang, the universe was almost perfectly smooth. Matter was spread out nearly evenly in all directions. But there were tiny fluctuations, microscopic variations in density that would eventually grow into everything we see today. Gravity did the rest. Regions that were slightly denser than average pulled in more matter from their surroundings. Over billions of years, these dense regions grew denser still, while the spaces between them emptied out. Matter flowed along invisible channels, accumulating into filaments and sheets, leaving behind the great voids that now dominate the cosmic landscape. This process is called gravitational collapse, and it is how structure forms in the universe. But gravitational collapse has limits. It takes time. Matter can only flow so fast, can only accumulate so quickly. The universe is only 13.8 billion years old. That sounds like an incredibly long time. But in cosmic terms, it is barely enough for the structures we see to have formed. Our mathematical models tell us exactly how large structures can possibly get given the age of the universe and the speed at which matter can flow. There is a fundamental limit, a cosmic speed limit for structure formation. The largest structures allowed by our models are around 1.2 billion light-years across. Anything bigger than that simply should not exist. There has not been enough time since the Big Bang for gravity to pull together anything larger. This is not a guess or an approximation. It is a hard limit derived from the fundamental physics of our universe. So imagine the shock when astronomers discovered something far, far larger. The story of this discovery begins in the 1980s, when astronomers were just beginning to map the large-scale structure of the universe. Using new technologies and innovative survey techniques, they started cataloguing galaxies by the thousands, then by the millions. Each galaxy was a data point, and together they painted a picture of cosmic architecture that no one had ever seen before. One of the first great surprises came in 1989 with the discovery of the Great Wall. This was a vast sheet of galaxies stretching across 500 million light-years of space. It was the largest known structure at the time, and it pushed against the limits of what physicists thought was possible. But it did not quite break them. The Great Wall was huge, but it was still within the bounds of what our models allowed. Over the following decades, as surveys grew more comprehensive and telescopes more powerful, we kept finding larger structures. The Sloan Great Wall, discovered in 2003, stretched for 1.37 billion light-years. This was already pushing into uncomfortable territory, slightly larger than the theoretical maximum. But measurement uncertainties are always present in astronomy, and many scientists argued that the true size might be somewhat smaller than the initial estimates suggested. Then came the discoveries that truly shattered our expectations. In 2013, astronomers announced the discovery of the Hercules-Corona Great Wall. This structure, if it can even be called a single structure, spans an almost incomprehensible 10 billion light-years. That is more than 8 times larger than the theoretical maximum. It is so large that it accounts for roughly 1/10 of the diameter of the entire observable universe. Let me say that again, because it deserves to sink in. One single structure occupying roughly 1/10 of the entire observable universe. The observable universe is everything we can possibly see. the sphere of space from which light has had time to reach us since the beginning of time, and one structure fills 1/10 of that volume. But even the Hercules-Corona Great Wall is not the largest thing we have found. The search for these cosmic giants has continued, and the results have only grown more unsettling. In recent years, astronomers have identified structures that make even this 10 billion light-year monster look modest by comparison. The structure that truly broke our understanding is something called the giant arc. Discovered in 2021, this curved arrangement of galaxies, galaxy clusters, and gas spans 3.3 billion light-years. While smaller than the Hercules-Corona Great Wall, the giant arc is significant for a different reason. It is far more clearly defined, far more obviously a single coherent structure, and its arc-like shape suggests it might be part of something even larger, a ring or shell structure that we can only partially see. But wait, there is more, because the giant arc is not alone. Near it in the sky, astronomers have found another impossibly large structure called the Big Ring. This ring of galaxies, discovered in 2024, has a diameter of 1.3 billion light-years. It sits in the same general region of space as the giant arc, and the two structures appear to be connected in some way. Together, they hint at a cosmic architecture that we never imagined could exist. And then there is the discovery that truly defies comprehension. When astronomers looked even more carefully at the region containing the giant arc and the Big Ring, they found evidence of something even larger lurking in the background, something so vast that we can barely perceive its outlines, something that stretches across the entire field of view of our deepest surveys. This is the structure so large it broke our understanding of space. Not just one impossible object, but an entire network of impossible objects, woven together into a tapestry of cosmic proportions. The theoretical maximum has not just been exceeded, it has been obliterated. The rules we thought governed the universe appear to be fundamentally wrong, or at least deeply incomplete. So how do we even discover something like this? How do you find a structure that is billions of light-years across, scattered across the most distant reaches of the observable universe? The answer involves some of the most ingenious techniques in all of astronomy, and some of the most powerful explosions in the cosmos. The key to finding these giant structures is gamma-ray bursts. These are the most energetic events in the universe, explosions so powerful that they briefly outshine entire galaxies containing hundreds of billions of stars. A single gamma-ray burst releases more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. These cosmic fireworks are caused by the deaths of massive stars, or the collisions of ultra-dense objects like neutron stars. Because gamma-ray bursts are so bright, we can detect them from incredibly far away. They act like cosmic flashbulbs, briefly illuminating the distant universe and allowing us to see galaxies and structures that would otherwise be invisible. By mapping where gamma-ray bursts occur, astronomers can build up a picture of where matter is concentrated in the distant universe. When researchers analyzed the distribution of thousands of gamma-ray bursts, a pattern emerged. The bursts were not distributed randomly across the sky. Instead, they clustered in certain regions and were sparse in others. This clustering revealed the presence of enormous structures, concentrations of matter spanning billions of light-years. At first, many astronomers were skeptical. Surely the clustering must be a statistical fluke, a random pattern that our pattern-seeking brains interpreted as meaningful. But as more data accumulated, the signal only grew stronger. The structures were real. They were out there, impossibly large, impossibly coherent, impossibly defiant of everything we thought we knew. Now, let us pause here and really absorb what we are talking about. When I say these structures are billions of light years across, what does that actually mean? Let me try to give you some sense of the scale involved, though I warn you that no analogy can truly capture distances this vast. Our Sun is one star among roughly 400 billion in the Milky Way galaxy. If you could travel at the speed of light, it would take you 100,000 years to cross our galaxy from end to end. But our galaxy is just one of countless galaxies in the universe. The nearest major galaxy to us, Andromeda, is 2.5 million light-years away. Light that left Andromeda and arrived at Earth tonight began its journey before humans existed, before our ancestors had even evolved. The local group, the cluster of galaxies that includes the Milky Way and Andromeda, is about 10 million light-years across. The Virgo supercluster, the larger structure that contains the local group, spans about 100 million light-years. These are already scales that make our entire existence seem almost infinitely small. But the structures we are talking about dwarf even the largest superclusters. The giant arc is 3.3 billion light-years across. That is 33 times larger than the Virgo supercluster. That is roughly 1/4 of the diameter of the entire observable universe. Light that we receive from one end of the giant arc began its journey before the Earth existed, before the Sun existed, before most of the stars in our galaxy had even formed. And the Hercules-Corona Great Wall is 3 times larger still, 10 billion light-years. Light from its far side has been traveling toward us for billions of years before the first galaxies formed. We are seeing it as it existed in an era so ancient that the universe itself was young. These are not just big numbers. They represent a fundamental challenge to our understanding of reality. How can structures this large exist? What force could have assembled them? And what does their existence tell us about the nature of the cosmos? To understand why these structures are so troubling, we need to delve deeper into the physics of how structure forms in the universe. This is where things get truly interesting and where the implications of these discoveries become clear. The standard model of cosmology, the framework that describes how the universe evolved from the Big Bang to the present day, is called Lambda-CDM. Lambda stands for the cosmological constant, the mysterious dark energy that is causing the expansion of the universe to accelerate. CDM stands for cold dark matter, the invisible substance that makes up most of the matter in the universe. This model has been extraordinarily successful. It correctly predicts the cosmic microwave background, the faint afterglow of the Big Bang that we can still detect today. It explains the distribution of galaxies on small and medium scales. It matches observations of how fast the universe is expanding and how that expansion rate has changed over time. By almost every measure, Lambda-CDM is one of the most successful theories in the history of science. But Lambda-CDM also makes very specific predictions about the size of cosmic structures. It tells us that the universe should be homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. Isotropic means the same in every direction. This is called the cosmological principle, and it is one of the foundational assumptions of modern cosmology. The cosmological principle does not say the universe is perfectly uniform. Obviously, there are stars and planets and galaxies and clusters. But it says that if you zoom out far enough, all those variations should average out. At the larger scales, the universe should look roughly the same no matter where you are or which direction you look. There should not be preferred locations or directions. There should not be structures so large that they stand out from the cosmic background. Specifically, Lambda-CDM predicts that structures larger than about 1.2 billion light-years should not exist. Beyond that scale, the universe should appear smooth and featureless, like a perfectly mixed batter with no lumps. Any structure larger than this limit would violate the cosmological principle. It would mean the universe is not homogeneous after all. It would mean our most fundamental assumptions about the cosmos are wrong. And yet, here we are, staring at structures that are 3, 5, even 10 times larger than the supposed maximum. The universe has lumps that should not be there. The batter was not mixed as thoroughly as we thought. This is not a minor problem. The cosmological principle is not just an aesthetic preference or a simplifying assumption. It is built into the very mathematics of general relativity, Einstein's theory of gravity that forms the foundation of all modern cosmology. If the cosmological principle is wrong, then our equations might be leading us astray. The predictions we make about the fate of the universe, the conclusions we draw about dark energy and dark matter, could all be based on a flawed foundation. Some cosmologists have responded to these discoveries by questioning the measurements. Perhaps the structures are not as large as they appear. Perhaps what looks like a single coherent structure is actually several smaller structures that happen to line up from our perspective. After all, we are viewing the universe from a single vantage point. Earth and projection effects can create illusions. This is a reasonable concern, and astronomers have worked hard to address it. They have used multiple independent methods to verify the sizes and distances of these structures. They have applied statistical tests to determine whether the observed patterns could arise by chance. The results consistently support the conclusion that these structures are real and are genuinely as large as they appear. Another response has been to tweak the Lambda-CDM model, adjusting parameters to allow for slightly larger structures. But the adjustments required to accommodate a 10 billion light-year structure are not small tweaks. They require fundamental changes to our understanding of either dark matter, dark energy, or both. Some researchers have proposed that dark energy might not be constant after all, that it might vary in strength across different regions of space. Others have suggested modifications to the theory of gravity itself. These are radical proposals, and they carry their own problems. General relativity has been tested to extraordinary precision in countless experiments. Any modification would need to preserve all those successful predictions, while also allowing for the formation of impossibly large structures. But that is an extremely difficult needle to thread. Perhaps the most unsettling possibility is that we are simply missing something fundamental about how the universe works. Our models are based on the physics we can test in laboratories and observe in our cosmic neighborhood. But the universe is vast beyond comprehension, and there may be phenomena occurring at the largest scales that we have never encountered before. Perhaps there are forces or processes that only become significant over billions of light years, effects that are invisible in our local patch of space, but shape the cosmos at its grandest scales. Let us explore what we actually know about how these giant structures might have formed. Even if we cannot fully explain them within our current understanding, we can at least try to understand what mechanisms might be at play. The starting point for structure formation is the quantum fluctuations that occurred during cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, stretching faster than the speed of light. During this inflationary epoch, random quantum variations in the energy density of space were stretched to cosmic proportions. These became the seeds of all future structure. Think of it like taking a smooth rubber sheet and rapidly stretching it. Any tiny imperfections in the rubber would be magnified enormously. What was once a microscopic bump would become a visible ridge. The quantum fluctuations in the early universe were like those tiny imperfections, and inflation was the stretching process that made them cosmic in scale. After inflation ended, gravity took over. Regions that were slightly denser than average began to attract more matter. Over millions and billions of years, these dense regions grew denser still. Gas collapsed to form stars. Stars gathered into galaxies. Galaxies clustered into groups and clusters. Clusters assembled into the filaments and sheets of the cosmic web. This process is called hierarchical structure formation, and it proceeds from small scales to large. First, you build atoms. Then you build molecules. Then you build dust grains and rocks and planets. Then you build stars and solar systems. Then you build galaxies and galaxy clusters. Each level of structure forms from the assembly of smaller components. But here is the problem. Hierarchical structure formation takes time, and time is limited by the age of the universe. You cannot build a 10 billion light-year structure by slowly assembling smaller pieces when the universe is only 13.8 billion years old. The math simply does not work out. Even if matter had been flowing toward these regions since the very beginning of time, traveling at the maximum possible speed, there would not be enough time to accumulate so much material. This temporal constraint is one of the hardest limits in cosmology. It comes directly from the speed of light, from the age of the universe, and from the basic laws of physics. For a structure to be gravitationally bound, to be a single coherent object rather than just a random alignment, the different parts of the structure need to have interacted with each other. Information needs to have been exchanged. Gravity needs to have had time to do its work. For a structure that is 10 billion light-years across, that means gravity would need to have been acting for 10 billion years just for one side to feel the gravitational influence of the other. But the universe is only 13.8 billion years old, and structure formation could not begin until the universe had cooled enough for matter to clump together. That happened a few 100 million years after the Big Bang, leaving maybe 13 billion years for structure to form. That is barely enough. Time for opposite ends of a 10 billion light-year structure to even know the other end exists, let alone to have been pulled together by gravity. So how can these structures exist? There are several possibilities, none of them entirely satisfying. One possibility is that these are not actually gravitationally bound structures at all. Perhaps what we are seeing are simply alignments of smaller structures that happen to fall along our line of sight. The universe is full of coincidences, and given enough volume to search, you might expect to find some apparent patterns just by chance. But astronomers have tested this hypothesis carefully, and the statistical significance of these structures is too high to be explained by random chance. The probability of the giant arc arising from a random distribution of galaxies is less than 1 in 10,000. For the Hercules-Corona Great Wall, the probability is even lower. These structures are real, not statistical flukes. Another possibility is that the seeds of these structures were much larger than we thought. Perhaps the quantum fluctuations during inflation were not as random as our models suggest. Perhaps some regions received a much larger initial boost, giving them a head start on structure formation. If certain regions were already significantly denser than average, by the time structure formation began, they might have been able to grow into supermassive structures even in the limited time available. This would require revising our understanding of inflation, the process that supposedly smoothed out the early universe, while also creating the seeds of structure. Inflation is already one of the most speculative aspects of cosmology, and our direct evidence for it is limited. It is possible that the inflationary process was more complex than our simple models suggest, allowing for occasional supermassive seeds that would later grow into these cosmic giants. A third possibility is that our understanding of dark matter is incomplete. Dark matter makes up about 27% of the total energy content of the universe, far outweighing ordinary matter like atoms and molecules. Dark matter interacts gravitationally, but not electromagnetically, which means it can clump together without being hindered by the radiation pressure that affects ordinary matter. In the standard model, dark matter particles are cold, meaning they move slowly compared to the speed of light. This allows them to clump together efficiently on galactic scales. But perhaps there is another component of dark matter that we have not detected, something that operates on larger scales and can seed the formation of supermassive structures. Some theorists have proposed warm dark matter or fuzzy dark matter, particles with different properties that might behave differently at the larger scales. A fourth possibility, perhaps the most radical, is that dark energy is not uniform throughout the universe. In the standard model, dark energy has the same density everywhere in space. It acts like a cosmic constant, pushing the universe apart at an accelerating rate. But what if dark energy varies from place to place? What if some regions of the universe have less dark energy than others, allowing structures to grow larger before the accelerating expansion tears them apart? This would violate one of the simplest assumptions of Lambda-CDM, but it might explain the existence of impossibly large structures. Regions with less dark energy would be like cosmic safe harbors, places where matter could accumulate for longer before being dispersed by the accelerating expansion. Over billions of years, these regions might grow into the giant structures we observe. There is even a more exotic possibility. Some theorists have suggested that these structures might be remnants of earlier cosmological epochs, perhaps even from before the Big Bang in our region of space. If the universe goes through cycles of expansion and contraction, or if our observable universe is just one bubble in a larger multiverse, then perhaps these structures carry information from previous cycles or from neighboring bubble universes. This idea is highly speculative, verging on science fiction. We have no direct evidence for cosmological cycles or bubble universes. But the existence of impossibly large structures is itself evidence that something unexpected is happening, and sometimes the most puzzling observations demand the most radical explanations. Whatever the explanation turns out to be, the implications are profound. These giant structures are not just curiosities, interesting facts to mention at dinner parties. They are fundamental challenges to our understanding of the universe. They tell us that our models, as successful as they have been, are incomplete. They point toward new physics that we have not yet discovered. Let us now turn to some of the specific structures that have been discovered and examine them more closely. Each one has its own story, its own peculiarities, and its own challenges for our understanding. We will start with the Sloan Great Wall, one of the first supermassive structures to be discovered and characterized in detail. Named after the Sloan Digital Sky Survey that revealed it. This wall of galaxies stretches for about 1.37 billion light-years, making it slightly larger than the theoretical maximum allowed by Lambda-CDM. The Sloan Great Wall is located about 1 billion light-years from Earth, making it close enough to study in considerable detail. It contains thousands of galaxies and spans a region of sky that would take several hours to cross even at the speed of light. The galaxies in the wall are not distributed randomly, but form a distinct pattern, a sheet-like structure that is clearly coherent on the larger scales. What makes the Sloan Great Wall particularly interesting is its relationship to other structures in the nearby universe. It is connected to the CFA2 Great Wall, another large-scale structure discovered earlier, forming part of an extended network of filaments and sheets. Together, these structures suggest that the cosmic web continues to larger scales than our models predict, with the walls and filaments extending further and connecting more extensively than we expected. The Sloan Great Wall pushed against the theoretical limits, but did not decisively break them. The uncertainties in measuring its exact size left room for doubt. Perhaps it was slightly smaller than the initial estimates suggested. 12. Perhaps it was not a single coherent structure, but a combination of several smaller structures that happened to overlap. Scientists could accommodate the Sloan Great Wall within their models, even if it required stretching those models to their limits. But then came the discoveries that left no room for doubt. The Hercules-Corona Borealis Great Wall was announced in 2013, based on an analysis of gamma-ray burst locations. Unlike the Sloan Great Wall, which was found through direct surveys of galaxies, this structure was detected indirectly through the clustering of gamma-ray bursts in a particular region of the sky. Gamma-ray bursts occur in galaxies throughout the observable universe. By mapping where they occur and estimating their distances, astronomers can build up a three-dimensional picture of the matter distribution in the distant universe. When researchers examined the distribution of gamma-ray bursts in the direction of the constellations Hercules and Corona Borealis, they found a significant excess, a region where bursts were much more common than average. The excess extended across an enormous region of the sky, corresponding to a structure roughly 10 billion light-years across. That is almost an order of magnitude larger than the theoretical maximum. It spans roughly 1/10 of the entire diameter of the observable universe. It contains so much matter that its existence challenges our most fundamental assumptions about cosmology. The initial discovery of the Hercules-Corona Borealis Great Wall was met with skepticism. A structure this large seemed impossible. Critics pointed out that gamma-ray burst surveys can be affected by various biases. Perhaps the apparent clustering was an artifact of how the observations were made. Perhaps certain regions of the sky were observed more intensely than others, creating an artificial excess. But subsequent analyses addressed these concerns. Researchers controlled for observational biases, applied different statistical methods, and examined the data from multiple angles. The structure persisted. It was not an artifact. Something genuinely massive was lurking out there in the distant universe. The implications were staggering. If a structure this large exists, then either our measurements of cosmic distances are somehow wrong, or our theories of structure formation are incomplete. Given that distance measurements in cosmology have been refined over decades using multiple independent methods, most scientists concluded that the problem lies with our theories. The Hercules-Corona Borealis Great Wall is so large that it challenges the cosmological principle at its core. If we draw a sphere around this structure, one that is supposed to be large enough for the universe to appear homogeneous, the sphere would be distinctly lumpier than our models predict. The universe, at least in this direction, is not as smooth as we thought. But perhaps the most unsettling aspect of the Hercules-Corona Borealis Great Wall is its age. The gamma-ray bursts that revealed it occurred at distances of 2 to 3 billion light-years and beyond. We are seeing this structure as it existed billions of years ago, when the universe was younger and had had even less time for structure to form. If such a massive structure existed that early in cosmic history, then the conditions for structure formation must be very different from what we assumed. Some astronomers have proposed that the Hercules-Corona Great Wall might not be a single coherent structure at all. Perhaps it is a chance alignment of several large-scale structures along our line of sight, creating the illusion of a single giant wall. This would still require structures larger than expected, but it would reduce the magnitude of the problem. However, even this explanation has difficulties. The concentration of gamma-ray bursts in this region is so pronounced that random alignment seems unlikely. Furthermore, the structure appears to have a coherent shape, a wall-like configuration that suggests genuine physical connection rather than mere projection effects. The mystery of the Hercules-Corona Great Wall remains unresolved. It stands as one of the greatest challenges to our understanding of cosmic structure, a giant question mark written across 1/10 of the observable universe. Now, let us turn to the more recent discoveries that have added new dimensions to this puzzle. In 2021, astronomers announced the discovery of the giant arc, a curved arrangement of galaxies, galaxy clusters, and gas that spans 3.3 billion light-years. Unlike the Hercules-Corona Great Wall, which was detected through gamma-ray burst clustering, the giant arc was found through a different method, the absorption patterns in the light of distant quasars. Quasars are extremely bright, objects powered by supermassive black holes at the centers of distant galaxies. They are so luminous that they can be seen across billions of light-years, and their light carries information about everything it passed through on its journey to Earth. When quasar light passes through clouds of gas between galaxies, certain wavelengths are absorbed by atoms in the gas. By analyzing these absorption patterns, astronomers can map the distribution of intergalactic gas. This technique revealed a remarkable pattern. Across a wide swath of sky, the absorption features lined up in a way that suggested a coherent structure, not a random distribution of gas clouds, but an organized arrangement forming a graceful arc across the cosmos. The giant arc was born. What makes the giant arc particularly intriguing is its shape. Most large-scale structures are either walls, filaments, or clusters. They are roughly linear or sheet-like, the kinds of shapes you would expect from gravitational collapse acting on random initial conditions. But the giant arc is different. It curves. It bends through space like a segment of an enormous ring or shell. This curved shape has led some astronomers to speculate that the giant arc might be part of something even larger. Perhaps it is a visible portion of a vast ring structure that extends beyond our surveys. Perhaps it is the edge of an enormous bubble, a spherical arrangement of matter surrounding a giant void. These possibilities are speculative, but the unusual shape demands unusual explanations. The discovery of the giant arc was stunning enough on its own. But then, just a few years later, astronomers found something even more remarkable nearby. In 2024, researchers announced the discovery of the Big Ring, a nearly circular arrangement of galaxies with a diameter of about 1.3 billion light-years. The Big Ring is located in roughly the same region of sky as the giant arc, leading to immediate speculation that the two structures might be connected. The proximity of these two structures is almost certainly not a coincidence. The giant arc and the Big Ring are separated by only about 12 degrees on the sky, a remarkably small angular distance for two of the largest structures ever discovered. Either we have stumbled upon an extraordinarily dense region of giant structures or these objects are physically related in some way. One possibility is that both structures are part of the same underlying formation, a vast assembly of matter that manifests in different ways at different distances. The giant arc might be a distant portion of an enormous shell, while the big ring might be a nearer cross-section of the same or a related structure. Together, they might trace out a cosmic architecture far more complex than anything we have previously imagined. Another possibility is that this region of space is somehow special, a place where conditions favored the formation of unusually large structures. Perhaps the initial density fluctuations in this region were stronger than average, providing larger seeds for structure formation. Perhaps local variations in dark matter or dark energy created conditions conducive to giant structure growth. Whatever the explanation, the discovery of two impossible structures in the same region of sky has profound implications. It suggests that these objects are not isolated anomalies, but symptoms of something more fundamental. If our theories are wrong, they are not just slightly wrong in one exceptional case. They are wrong in a systematic way that allows giant structures to form throughout the cosmos. The research team that discovered the Big Ring was led by Alexia Lopez, a doctoral student at the University of Central Lancashire. Her team used the same quasar absorption technique that revealed the giant arc, mapping the distribution of magnesium in intergalactic gas. The ring-like pattern that emerged from the data was unmistakable, a nearly perfect circle of enhanced magnesium absorption, indicating a coherent structure. Lopez and her colleagues were careful to rule out alternative explanations. They tested whether the ring could be a statistical fluke, a random arrangement of gas clouds that happened to form a circle by chance. The probability was vanishingly small, far less than 1%. They checked for observational artifacts, biases in how the data was collected or analyzed. They found none. The Big Ring, like the giant arc before it, appears to be a genuine feature of the cosmic landscape. The combined existence of the giant arc and the Big Ring poses severe challenges to the standard cosmological model. Not only do these structures individually exceed the theoretical size limit, but their proximity to each other suggests that giant structures might be more common than we thought. Our surveys have only examined a fraction of the observable universe in sufficient detail to detect such structures. If two impossibly large objects can be found in a single patch of sky, how many more might be lurking in the regions we have not yet studied? This question becomes even more pressing when we consider the third major discovery in this region, the hint of an even larger underlying structure connecting the giant arc and the Big Ring. When astronomers analyzed the full distribution of absorption features in this area, they noticed something troubling. The patterns did not stop at the boundaries of the giant arc and the Big Ring. They extended further, suggesting that these visible structures might be just the most prominent features of something far more extensive. Like mountain peaks rising above the clouds, the giant arc and the Big Ring might be the visible portions of a vast cosmic landscape that remains largely hidden from view. Some researchers have proposed that we might be seeing the edge of an enormous void, a giant bubble in the cosmic web where matter has been displaced to the surrounding regions. The giant arc and the Big Ring could be parts of the shell surrounding this void, concentrations of matter at the boundary between the empty bubble and the denser regions beyond. Voids are a natural consequence of cosmic structure formation. As matter flows toward dense regions, it leaves behind empty spaces that can grow to enormous sizes. The Bootes void, for example, is a nearly spherical region of empty space about 330 million light-years in diameter. If voids can grow this large, perhaps they can grow even larger, creating the conditions for giant ring and arc structures at their boundaries. But even this explanation has problems. The theoretical limits on structure size apply to voids as well as to concentrations of matter. A void so large that its boundary structures span billions of light years would itself violate the cosmological principle. We would simply be trading one impossible structure for another. Let us pause here and consider what all of this means for our place in the universe. For centuries, astronomy has repeatedly humbled humanity. We learned that Earth is not the center of the solar system, that the Sun is not the center of the galaxy, that our galaxy is not the center of the universe. Each discovery pushed us further from any special position, reinforcing the cosmic mediocrity principle. The idea that our location in the universe is nothing special. The discovery of giant cosmic structures adds a new dimension to this humbling. We are not just small compared to stars and galaxies and galaxy clusters. We are infinitesimally small compared to structures that span significant fractions of the observable universe. The giant arc alone contains more galaxies than we can count, more stars than there are grains of sand on all the beaches of Earth, more matter than we can comprehend. And it is just one structure among potentially many. But there is another way to look at these discoveries, a way that emphasizes wonder rather than insignificance. The universe contains structures so vast and so complex that we never imagined they could exist. The cosmos is stranger and more magnificent than our theories predicted. Every time we think we understand the universe, it surprises us with something new. The giant arc and the big ring and the Hercules-Corona Great Wall are not just challenges to our understanding. They are invitations to discovery. They are hints that there is more to learn, more to explore, more to understand. The universe has not revealed all its secrets. Perhaps the greatest discoveries are still ahead. Now let us delve deeper into what these structures might tell us about the fundamental nature of reality. If our standard models are wrong, what might replace them? What new physics could explain the existence of structures that should be impossible? One intriguing possibility involves cosmic strings, theoretical objects that might have formed in the early universe when space itself underwent phase transitions. Think of cosmic strings like cracks that form in ice when water freezes. As the universe cooled after the Big Bang, the quantum fields that permeate space might have settled into different states in different regions. The boundaries between these regions could form one-dimensional defects, strings of incredibly dense energy stretching across cosmic distances. If cosmic strings exist, they would be among the strangest objects in the universe. They would be thinner than an atom, but contain more mass per unit length than millions of suns. Their gravitational effects would be unusual, bending space in ways that differ from ordinary matter. And crucially, they could provide seeds for structure formation that circumvent the normal limits. A cosmic string stretching across billions of light years would create a gravitational disturbance along its entire length. Matter would be attracted toward the string from all directions, accumulating along its path. Over time, this could create the enormous wall and arc-like structures that we observe. The giant arc, with its curved shape, could even be interpreted as matter accumulating around a curved cosmic string. The idea is speculative, but it is not without support. Cosmic strings are a generic prediction of many theories that go beyond the standard model of particle physics. If these theories are correct, cosmic strings should have formed in the early universe and should still be present today. The fact that we have not yet detected them directly could simply mean they are rare or difficult to observe, not that they do not exist. Another possibility involves primordial magnetic fields, magnetic structures that might have formed in the very early universe before the first stars and galaxies. We know that magnetic fields exist on galactic scales today, but their origin is uncertain. Some theories suggest that weak magnetic fields were present from the earliest moments of cosmic history, gradually amplified by the motions of matter over billions of years. Primordial magnetic fields could influence structure formation in subtle but important ways. Magnetic pressure could resist gravitational collapse in some regions while enhancing it in others, creating patterns of structure that differ from pure gravitational models. If the primordial magnetic field had large-scale coherence, it could have seeded the formation of giant structures that retain that coherence today. A third possibility involves modifications to our theory of gravity itself. General relativity has been tested with extraordinary precision in the solar system and in binary pulsar systems, but these tests probe relatively small scales. On the larger scales, where giant cosmic structures reside, we have far less direct evidence about how gravity behaves. Some physicists have proposed that gravity might weaken at very large distances, an effect that would not be detectable in local experiments, but could dramatically change the dynamics of cosmic structure. If gravity is slightly weaker than expected over billions of light years, structures could grow larger before being disrupted by the expansion of the universe. This could allow the formation of structures that would be impossible in standard general relativity. Modified gravity theories come in many varieties, with names like MOND, F of R gravity, and massive gravity. Each modifies Einstein's equations in different ways, with different predictions for how the universe should behave on large scales. The discovery of giant cosmic structures provides new constraints on these theories, ruling out some modifications while potentially supporting others. Perhaps the most radical possibility involves questioning our assumptions about the geometry of the universe itself. In standard cosmology, we assume that the universe is homogeneous and isotropic on large scales, and that the spatial geometry is flat or nearly so. But what if these assumptions are wrong? If the universe has a more complex geometry than we thought, with regions of positive and negative curvature distributed throughout space, then the distances we measure to distant objects could be systematically incorrect. What appears to be a 10 billion light-year structure might actually be smaller, seen through a cosmic lens that magnifies its apparent size. Or alternatively, the universe might be much larger than we think, with our observable portion being just a small and possibly unrepresentative sample. These geometric possibilities are difficult to test directly, but they cannot be ruled out. Our measurements of cosmic geometry are based on the cosmic microwave background and the distribution of galaxies, both of which assume that we understand how light propagates through the universe. If there are geometric effects we have not accounted for, our conclusions could be systematically biased. The existence of giant cosmic structures has motivated a wide range of new theoretical work, with researchers exploring possibilities that would have seemed outlandish just a few decades ago. This is how science progresses. Unexpected observations force us to question our assumptions and consider new ideas. The structures so large they broke our understanding might ultimately lead to a deeper and more accurate understanding of the cosmos. Let us take a step back now and examine the cosmic web itself in more detail. Understanding this grand architecture is essential to appreciating why the giant structures are so surprising and what they might mean for our cosmic future. The cosmic web is not something we can see directly with our eyes. Most of its mass is dark matter, invisible stuff that interacts with nothing except through gravity. The galaxies that we can see are like lights strung along the dark matter scaffolding, decorations that reveal the underlying structure but represent only a small fraction of the total mass. To map the cosmic web, astronomers use several complementary techniques. The most direct is simply to survey millions of galaxies, measuring their positions and distances. By building up a three-dimensional map of galaxy locations, we can see where the cosmic web's filaments and nodes lie. This is how the Sloan Digital Sky Survey revealed structures like the Sloan Great Wall, patiently cataloguing galaxies one by one until patterns emerge from the data. But galaxy surveys only show us where the luminous matter is concentrated. To see the full cosmic web, including the dark matter that dominates its mass, we need other techniques. One powerful method is gravitational lensing. Massive objects bend light that passes near them, distorting the images of more distant galaxies. By carefully measuring these distortions across the sky, astronomers can reconstruct the distribution of mass along the line of sight, whether that mass is visible or dark. This technique has revealed the dark matter scaffolding of the cosmic web, confirming that galaxies do indeed trace underlying dark matter structures. Another method uses the distribution of neutral hydrogen gas, the most common element in the universe. Before hydrogen gets incorporated into stars, it exists as diffuse gas in intergalactic space, spread along the filaments of the cosmic web. By mapping this gas using radio telescopes or absorption studies, astronomers can trace the web's structure even in regions where few galaxies are visible. The cosmic web has a characteristic scale, a typical distance between its filaments and nodes. This scale is set by the physics of structure formation, by the balance between gravity pulling matter together and the expansion of the universe spreading it apart. The typical filament is a few tens of millions of light years long, connecting nodes that contain galaxy clusters with hundreds or thousands of member galaxies. But these typical scales are just averages. The cosmic web is not a regular grid with uniform spacing. It has a wide range of structures, from tiny tendrils connecting individual galaxies to vast walls stretching across hundreds of millions of light years. This variation is expected in hierarchical structure formation, where random initial conditions lead to a wide distribution of structure sizes. What the giant structures challenge is not the existence of variation, but the extreme tail of the distribution. Our models predict that variations should become smaller as we go to larger scales, eventually averaging out to a smooth, uniform distribution. The giant structures violate this expectation, showing that the universe remains lumpy at scales far larger than predicted. To visualize what the cosmic web looks like, imagine a three-dimensional spider web floating in space. The strands of the web are the filaments where galaxies concentrate. The nodes where strands meet are the galaxy clusters, the densest regions of the cosmic web. The spaces between the strands are the voids, vast regions of almost empty space. Now imagine zooming out further and further. At first, you see the intricate detail of individual filaments, the galaxies strung along them like pearls on a string. As you zoom out more, the individual galaxies blur together, and you see only the overall pattern of the web. Keep zooming, and eventually the web should fade into a uniform grey, all the structure averaged out into smooth uniformity. But what the giant structures tell us is that this final smoothing does not happen when it should. Even at scales of billions of light years, there are still patterns visible, still concentrations and voids that stand out from the average. The universe is lumpy all the way up, far lumpier than it has any right to be. This persistent lumpiness has implications beyond just challenging our models. It affects how we interpret other cosmological measurements. Many of our conclusions about dark matter and dark energy are based on the assumption that we can average over large enough volumes to get representative samples of the universe. If the universe is lumpier than expected, these averages might be misleading. Consider, for example, measurements of the expansion rate of the universe. Astronomers have found a discrepancy between local measurements of the expansion rate based on observations of nearby supernovae and galaxies, and more distant measurements based on the cosmic microwave background. This tension, known as the Hubble tension, is one of the biggest puzzles in modern cosmology. Some researchers have proposed that the Hubble tension might be related to large-scale structure. If we happen to live in a slightly underdense region of the universe, a small void embedded in the cosmic web, then the expansion rate we measure locally might differ from the cosmic average. Local underdensities would cause matter to flow outward, adding to the apparent expansion rate and making the universe seem to be expanding faster than it actually is. The giant cosmic structures provide evidence that such local variations in density might be larger than previously thought. If structures can be truly giant, so can voids. We might be living in a void large enough to significantly bias our local measurements, creating apparent discrepancies with more distant observations. This is speculative, of course. The Hubble tension has many proposed explanations, and we do not yet know which, if any, is correct. But it illustrates how the discovery of giant structures connects to other puzzles in cosmology. Everything in the universe is interconnected, and surprises in one area often have implications for others. Let us now explore how the cosmic web influences the galaxies within it. The structures we have been discussing are not just passive backdrops against which cosmic evolution plays out. They are active participants in the story, shaping the fates of the galaxies they contain. Galaxies in dense regions of the cosmic web evolve differently from galaxies in sparse regions. Dense environments tend to host older, redder galaxies that have stopped forming new stars. Sparse environments tend to host younger, bluer galaxies that are still actively creating stars. This correlation between galaxy properties and environment is one of the fundamental patterns in extragalactic astronomy. The reason for this correlation involves both nature and nurture. Galaxies in dense regions formed earlier, when the universe was younger and denser overall. They also experience more interactions with neighboring galaxies, collisions and mergers that can strip away gas and trigger bursts of star formation that exhaust their fuel. Over time, these effects transform active star-forming galaxies into passive elliptical galaxies dominated by old red stars. The filaments of the cosmic web act like cosmic highways, channeling galaxies toward the dense nodes at filament intersections. As galaxies fall along filaments, they experience ram pressure from the intergalactic gas, tidal forces from nearby mass concentrations, and occasional close encounters with other galaxies. By the time they reach the cluster nodes, many have been transformed from their original state. This process of environmental transformation happens across the entire cosmic web, from the smallest filaments to the largest walls. The giant structures we have discovered must contain enormous numbers of galaxies, all subject to these environmental effects. The evolutionary histories of these galaxies would be shaped by their location within the giant structure, their position along the vast filaments and walls. Some researchers have speculated that galaxies within giant structures might have properties that differ systematically from galaxies elsewhere. Perhaps the environmental effects are stronger or weaker in these unusual regions. Perhaps the formation history was different, leading to different populations of stars and different chemical compositions. As surveys improve, we might be able to test these predictions and learn more about how the giant structures formed and evolved. Another fascinating aspect of the cosmic web is its connection to the cosmic microwave background, the oldest light in the universe. The cosmic microwave background was emitted about 380,000 years after the Big Bang, when the universe first became transparent to light. Before that, the universe was a hot, dense plasma, and light could not travel freely without being scattered by electrons. When the plasma cooled enough for atoms to form, light suddenly could travel unimpeded, creating a flash that we still see today as the cosmic microwave background. The cosmic microwave background is remarkably uniform. The same temperature in every direction, too, within about 1 part in 100,000. But those tiny temperature variations are incredibly important. They reflect the density variations in the early universe, the seeds from which all future structure would grow. Regions that were slightly hotter than average corresponded to slightly less dense regions, while regions that were slightly cooler corresponded to slightly denser regions. By mapping the cosmic microwave background in exquisite detail, astronomers have measured the initial conditions for structure formation. These measurements place tight constraints on cosmological parameters, telling us how much dark matter and dark energy the universe contains, how fast it is expanding, and what the geometry of space looks like. The standard cosmological model, Lambda-CDM, successfully predicts the observed pattern of cosmic microwave background fluctuations. This is one of the great triumphs of modern cosmology, a quantitative match between theory and observation that spans billions of years of cosmic evolution. But the giant structures pose a challenge to this picture. If the universe developed structures far larger than Lambda-CDM predicts, then the initial conditions encoded in the cosmic microwave background must have been different from what we assumed. Either the fluctuations were larger at some scales than we measured, or some additional process-enhanced structure growth beyond what standard gravity would allow. In either case, our interpretation of the cosmic microwave background might need revision. Some researchers have looked for signatures of giant structures in the cosmic microwave background itself, searching for patterns that might correspond to these enormous features. The results have been intriguing but not conclusive. There are hints of large-scale anomalies in the microwave background, regions where the temperature fluctuations do not quite match the standard predictions. Whether these anomalies are related to the giant structures remains an open question. One particularly puzzling feature is the cold spot, a region in the cosmic microwave background that is significantly colder than its surroundings. The cold spot is about 5 degrees across on the sky, far larger than typical fluctuations. Its existence was unexpected and has never been fully explained. Some astronomers have proposed that the cold spot might be caused by a giant void along the line of sight. As photons from the cosmic microwave background travel through a void, they lose energy in a way that makes the void appear colder than average. This explanation requires a void about 1 billion light-years across, large but not unprecedented, given the structures we have been discussing. The connection between the cold spot and giant cosmic structures is still being investigated. If confirmed, it would provide another piece of evidence that the universe is lumpier at large scales than expected, with voids and structures extending to sizes that challenge our models. Let us now consider the dark matter aspect of these giant structures in more detail. dark matter makes up the bulk of the mass in the cosmic web, roughly 5 times more than ordinary matter. Without dark matter, the cosmic web as we know it would not exist. Ordinary matter alone could not have clumped together fast enough to create the structures we see today. Dark matter particles do not interact with light, which is why we call them dark. They do not emit, absorb, or scatter photons. The only way we can detect dark matter is through its gravitational influence, the way it pulls on ordinary matter and bends light passing nearby. This gravitational influence has been mapped extensively using various techniques. Gravitational lensing surveys have traced dark matter around individual galaxies, in galaxy clusters, and across large swaths of sky. The results consistently show that dark matter is distributed in a cosmic web pattern, with filaments and nodes that trace the locations of visible galaxies. But the dark matter web is not identical to the galaxy web. Dark matter is more smoothly distributed, extending beyond the concentrated regions where galaxies are found. The filaments of dark matter are wider than the chains of galaxies they contain, like rivers that are broader than the boats floating on them. This difference in distribution is important for understanding the giant structures. When we detect giant walls and arcs of galaxies, we are seeing the visible traces of even larger dark matter concentrations. The true extent of these structures, measured in dark matter rather than visible galaxies, might be even larger than we realize. Some simulations of cosmic structure formation have attempted to create structures as large as the Hercules-Corona Great Wall. Most have failed. Standard simulations using Lambda-CDM physics consistently produce cosmic webs with structure up to about 1 billion light-years, but nothing larger. This failure is not a quirk of particular simulations, but a fundamental prediction of the standard model. To produce giant structures in simulations, researchers have had to modify the initial conditions or the physical laws governing structure growth. Some have used initial fluctuations with enhanced power at large scales, providing larger seeds for structure formation. Others have modified gravity or dark matter properties to allow faster or more extensive structure growth. These modified simulations can produce giant structures, but at the cost of departing from the standard model. The challenge for any modified model is to reproduce all the observations, not just the giant structures. The standard model is successful because it matches a wide range of data, from the cosmic microwave background to galaxy clustering to supernova distances. Any modification must preserve these successes, while also explaining the anomalies. This is a difficult balancing act, and no modified model has yet achieved it convincingly. This is why the giant structures remain a puzzle. They are real. Their existence has been confirmed by multiple independent observations, but we do not have a satisfying theoretical framework to explain them. They hang over cosmology like an unsolved mystery, challenging us to think deeper and question our assumptions. What does it feel like to contemplate structures so large that they break our understanding? For many people, the first reaction is a kind of vertigo, a dizzying sense of scale that makes ordinary concerns seem impossibly small. The problems that occupy our daily lives, the worries about work and relationships and health, what are they compared to walls of galaxies stretching across billions of light years? But there is another way to respond to these discoveries, a way that finds meaning rather than insignificance. We are the creatures who discovered these structures. We are the matter that woke up and looked at itself, tiny specks of organized atoms that somehow developed the curiosity and intelligence to map the cosmos. In a universe filled with giant structures and impossible scales, consciousness might be the most remarkable phenomenon of all. Think about what it means to understand a structure 10 billion light-years across. The light from the far side of the Hercules-Corona Borealis Great Wall has been traveling for most of cosmic history. It left its source before the Earth existed, before the Sun formed, before most of the heavy elements in our bodies were synthesized in stellar furnaces. And yet, here we are, on this small blue planet, receiving that ancient light and decoding its message. Every measurement we make, every pattern we detect, is a bridge across unimaginable distances of space and time. The gamma-ray bursts that revealed the Hercules-Corona Borealis Great Wall were explosions that occurred billions of years ago, cataclysmic deaths of massive stars in galaxies so distant we will never see them directly. Yet their light reached us, and we had the tools and knowledge to make sense of it. This is the miracle of science, that small, finite beings can comprehend the infinite. Our brains evolved to track fruit and predators across African savannas, not to conceptualize structures spanning significant fractions of the observable universe. And yet we can do it. We can take the raw data of our senses, extend them with instruments and mathematics, and build mental models of realities that lie far beyond our direct experience. The giant cosmic structures remind us that the universe does not exist for us. It was not created with human scales in mind. The cosmos operates according to its own rules, on its own timescales, at its own dimensions. We are latecomers to a vast story that began billions of years before our arrival and will continue billions of years after our departure. But being latecomers does not diminish us. If anything, it makes our achievements more remarkable. In the cosmic blink of an eye that has been human civilization, we have learned to read the book of nature, to decipher the laws that govern everything from atoms to galaxies. The giant structures are chapters in that book that we are just beginning to understand. Let us consider what the future might hold for our understanding of these cosmic giants. The next decade promises revolutionary new observations that could either confirm or overturn our current picture of large-scale structure. Several major surveys are underway or planned that will dramatically expand our knowledge of the cosmic web. The Dark Energy Spectroscopic Instrument, or DESI, is currently mapping the positions and distances of tens of millions of galaxies, building the most detailed three-dimensional map of the universe ever created. The Vera Rubin Observatory, scheduled to begin full operation soon, will survey the entire visible sky repeatedly, discovering billions of new objects and tracking how they change over time. These surveys will probe structure at scales and distances never before accessible. If giant structures like the Hercules-Corona Borealis Great Wall are common, these surveys will find more of them. If they are rare, the surveys will tell us just how rare, constraining theories about their formation. Either way, we will learn something important. The Euclid Space Telescope, launched by the European Space Agency, is mapping the distribution of dark matter across a third of the sky using gravitational lensing. This will reveal the dark matter scaffolding of the cosmic web with unprecedented clarity, showing us the true extent of structures that we currently see only through their visible galaxy tracers. Radio surveys using arrays like the Square Kilometre Array will map neutral hydrogen across cosmic history, tracing the fuel from which galaxies formed. These observations will show how the cosmic web evolved over time from the smooth early universe to the intricate structure we see today. And gravitational wave detectors, both on Earth and in space, might someday detect the imprint of giant structures on the ripples of space-time. As gravitational waves travel across billions of light years, they are subtly affected by the matter they pass through. In principle, this could provide a new way to map the cosmic web, complementing observations based on light. All of these observations will either confirm the standard cosmological model, showing that the giant structures are statistical flukes or measurement errors, or they will force us to revise our understanding. The coming years will be a decisive period for cosmology, a time when fundamental questions about the nature of the universe may finally be resolved. Of course, history teaches us that answers often lead to new questions. Even if we explain the giant structures within a modified framework, that framework will have its own puzzles and mysteries. Science does not end with solutions, but opens new horizons with each discovery. Let us now explore some of the more speculative ideas about what the giant structures might mean. These ideas go beyond what mainstream science currently accepts, but they are not beyond what thoughtful researchers have proposed. One intriguing speculation involves the multiverse, the idea that our observable universe is just one of many universes in a larger cosmic ensemble. In some multiverse theories, different universes can have different physical laws and different initial conditions. The universes might even interact in subtle ways, leaving imprints on each other's structure. Could the giant structures be evidence of such interactions? Could they be regions where our universe was influenced by a neighboring universe, perhaps through gravitational effects that leak across the boundary between them? This idea is almost impossible to test with current technology, but it cannot be ruled out. The universe is under no obligation to be simple or to make itself easy for us to understand. Another speculation involves the nature of space itself. In standard physics, space is a passive background against which events play out. But in some theories, space has its own dynamical properties, its own degrees of freedom that can become excited and influence the behavior of matter. Perhaps the giant structures are regions where space itself has unusual properties, remnants of processes that occurred in the very early universe. Loop quantum gravity, one of the leading approaches to quantum gravity, describes space as made up of discrete units, like atoms of geometry. In this picture, space is not continuous but granular at the smallest scales. At the larger scales, this granularity averages out, but perhaps not perfectly. Residual effects could create patterns in the distribution of matter that differ from classical predictions. String theory offers another perspective. In string theory, the fundamental constituents of reality are not particles, but tiny vibrating strings. These strings can exist in many different configurations, corresponding to the different particles and forces we observe. String theory also predicts the existence of higher dimensional objects called branes, surfaces on which strings can end. Some string theorists have proposed that our universe might be a brane floating in a higher dimensional space with other branes nearby. Gravitational effects from these neighboring branes could influence the distribution of matter in our universe, potentially creating structures that would not arise from internal processes alone. The giant cosmic structures could be shadows of geometry beyond our normal perception. These ideas are speculative, even by the standards of theoretical physics. We have no direct evidence for the multiverse, for space atoms, or for extra dimensions. But we also have no direct evidence that our current models are complete. The giant structures tell us that something unexpected is happening at the larger scales. Until we understand what that something is, we should keep our minds open to possibilities that might seem strange or unlikely. Let us return to Earth now and consider how the discovery of giant cosmic structures affects our cultural and philosophical outlook. Throughout human history, our understanding of our place in the cosmos has shaped our sense of meaning and purpose. The revelation that we live on a small planet orbiting an ordinary star in a vast galaxy among billions of galaxies has had profound psychological and philosophical effects. The giant structures add a new chapter to this story. We are not just small compared to galaxies and galaxy clusters. We are infinitesimally tiny compared to walls and arcs and rings that span significant fractions of the observable universe. The scale of creation exceeds anything our ancestors could have imagined, and continues to exceed our expectations even today. For some people, this vastness evokes a sense of cosmic loneliness. In all that space, on all those billions of planets circling all those trillions of stars, are we alone? The question of extraterrestrial life takes on new urgency when we contemplate structures containing countless opportunities for life to arise. If the universe is so vast and so structured, where is everyone? This is the Fermi paradox, the puzzling silence of a universe that should be teeming with intelligence. The giant structures do not resolve this paradox, but they deepen it. More space means more potential. More structures mean more complexity. Yet as far as we can tell, we remain alone, the only minds contemplating the cosmic immensity. Perhaps the answer involves the very scale we have been discussing. The universe may be vast, but the speed of light is finite. Signals and spacecraft cannot travel faster than light, which means that even the nearest stars are years away, and the nearest galaxies are millions of years away. The giant structures are billions of years across in light travel time. Even if intelligence is common in the universe, the distances may simply be too great for contact to be practical. Or perhaps intelligence is rarer than we assume. Perhaps the conditions that gave rise to minds on Earth are unusual, requiring a specific combination of circumstances that occurs only rarely even in a vast universe. The giant structures contain countless galaxies, but if only 1 in a trillion galaxies produces intelligence, the numbers might still leave us effectively alone. These are questions without definitive answers, at least for now, but they remind us that the study of cosmic structure is not just an abstract scientific pursuit. It connects to our deepest questions about who we are and what our existence means. Every new discovery about the large-scale universe is also a discovery about ourselves, our possibilities, and our limitations. The night sky has always been a mirror in which humanity sees itself reflected. Ancient peoples looked up and saw gods and heroes in the patterns of stars. Medieval astronomers saw the perfect geometry of divine creation. Modern scientists see the laws of physics written in light and motion and gravity. What will future generations see when they look up at a sky that contains structures so large they broke our understanding? Perhaps they will see evidence of a universe far stranger than we currently imagine. Perhaps they will have theories that make our puzzlement seem quaint. Frameworks that explain the giant structures as naturally as we explain planetary orbits. Or perhaps the mystery will endure, a permanent reminder that the cosmos is larger and more complex than any human mind can fully grasp. Either way, the journey of discovery continues. Every observation brings new data. Every analysis brings new insights. The giant structures are not the end of cosmology, but a new beginning, an invitation to push our understanding further than ever before. Now let us dive into some of the technical details of how astronomers actually measure these enormous distances. Understanding the techniques is essential to evaluating how confident we should be in the reality of the giant structures. Distance measurement in cosmology is notoriously difficult. We cannot stretch a tape measure to distant galaxies. We cannot send probes to measure how long the journey takes. We have to rely on indirect methods, each with its own assumptions and limitations. The most fundamental distance indicator is redshift, the stretching of light wavelengths caused by the expansion of the universe. As the universe expands, the space between galaxies grows, and light traveling through that space gets stretched to longer wavelengths. The more distant an object, the more its light has been stretched, and the greater its redshift. Redshift provides a measure of how much the universe has expanded since the light left the source. Combined with a model of how fast the universe has expanded over time, redshift can be converted into a distance. This conversion depends on cosmological parameters like the Hubble constant and the densities of matter and dark energy. Different assumptions give different distances. For the giant structures, the distances involved are so large that uncertainties in cosmological parameters become significant. A 10% uncertainty in the Hubble constant translates into a 10% uncertainty in the size of a structure. For the Hercules-Corona Borealis Great Wall, that could mean a difference of 1 billion light-years either way. However, even with generous uncertainties, the giant structures remain far larger than the theoretical maximum. The Hercules-Corona Borealis Great Wall could shrink by half and still be several times larger than allowed by standard models. The statistical evidence for the structure's existence is strong enough to survive reasonable adjustments to the distance scale. Another potential source of error involves the identification of structures themselves. How do we know that what appears to be a single giant wall is not actually several smaller walls that happen to overlap along our line of sight? The universe is three-dimensional, but our observations give us a two-dimensional view plus distance estimates that have their own uncertainties. Astronomers address this concern through careful statistical analysis. They compare the observed clustering of objects with what would be expected from random distributions. If the clustering is strong enough that random alignment is improbable, the structure is considered real. For the giant structures, these tests consistently favor reality over random alignment. But statistical tests have their own subtleties. The more data you examine, the more likely you are to find patterns just by chance. This is known as the look elsewhere effect, or multiple testing problem. If you examine 1,000 different regions of the sky, you might find one that shows unusual clustering just by random chance. Astronomers account for this by calculating the probability of finding a structure at least as unusual as the observed one anywhere in the surveyed volume. This is a more conservative test than asking about a specific pre-selected region. For the giant structures, even this conservative test gives probabilities well below 1%, suggesting that the structures are real rather than statistical flukes. Nevertheless, healthy skepticism is warranted. The history of astronomy includes examples of claimed structures that later turned out to be artifacts of observation or analysis. The giant structures have been confirmed by multiple independent teams using different data and methods, which increases confidence in their reality. But until we have a theoretical framework that predicts their existence, some uncertainty will remain. The interplay between observation and theory is at the heart of the scientific method. Observations motivate new theories, and theories make predictions that can be tested by new observations. For the giant structures, we have observations that challenge existing theory, creating a productive tension that drives research forward. This tension is uncomfortable but necessary. Science advances not when everything fits together neatly, but when there are puzzles to solve and anomalies to explain. The giant structures are among the most important anomalies in modern cosmology, problems that demand attention and might ultimately lead to revolutionary new understanding. Let us now explore how the giant structures connect to other mysteries in cosmology. The universe has many puzzles, and they may be related in ways we do not yet fully understand. One such mystery is the nature of dark energy, the force causing the expansion of the universe to accelerate. Dark energy makes up about 68% of the total energy content of the cosmos, yet we know almost nothing about what it actually is. In the Standard Model, dark energy is represented by a cosmological constant, a fixed energy density that permeates all of space. But this is essentially a placeholder, a parameter fit to observations rather than derived from fundamental physics. Some researchers have proposed that dark energy might not be constant, but might vary across space and time. In this picture, different regions of the universe could have different amounts of dark energy, affecting how structures form and evolve. Regions with less dark energy might allow larger structures to grow, while regions with more dark energy might suppress structure formation. Could the giant structures be located in regions where dark energy is unusually weak? This would explain how they managed to form despite the theoretical limits imposed by a uniform cosmological constant. The structures would essentially be cosmic oases, places where the accelerating expansion that normally tears structures apart is somehow diminished. This idea is speculative, but not entirely without support. Observations of the local expansion rate suggest that our cosmic neighborhood might be embedded in an underdense region, a local void where the expansion is slightly faster than average. If such variations exist at larger scales, they could create conditions favorable for giant structure formation. Another cosmic mystery involves the so-called axis of evil, an apparent alignment of patterns in the cosmic microwave background with the plane of the solar system. This alignment should not exist if the universe is truly homogeneous and isotropic. The microwave background comes from billions of light years away and should have no connection to our local geometry. Yet the alignment is there, puzzling astronomers for decades. The axis of evil has never been satisfactorily explained. Some researchers attribute it to systematic errors in the measurements or to statistical flukes. Others see it as evidence that the universe has a preferred direction, violating the cosmological principle that underlies Lambda-CDM. The giant structures might be related to this mystery. If the universe has large-scale structure that extends to the entire observable volume, that structure could create apparent alignments with local geometry. We might be located in a position where the giant structures happen to align with certain directions in our sky, creating the patterns we observe in the microwave background. This connection is highly speculative, but it illustrates how different cosmic anomalies might be linked. If the cosmological principle is violated, that violation could manifest in multiple ways, as giant structures, as preferred directions, as alignments that should not exist. A unified explanation for all these anomalies would be more compelling than separate explanations for each. Another mystery involves the distribution of matter on the larger scales. In the Standard Model, matter should be distributed in a specific statistical pattern, with fluctuations that decrease in amplitude at larger scales. This prediction is based on the physics of the early universe, when quantum fluctuations were imprinted on the cosmic background. But some observations suggest that matter fluctuations are larger than expected at the biggest scales. Galaxy surveys and cosmic microwave background measurements Both show hints of excess power at large scales, though the statistical significance is debated. The giant structures would fit naturally into this picture as extreme examples of large-scale fluctuations that exceed standard predictions. If these excess fluctuations are real, they would point toward new physics in the early universe. Perhaps inflation worked differently than we assume, generating larger seeds for structure formation. Perhaps there were additional processes before or during inflation that enhanced large-scale fluctuations. The giant structures might be fossil evidence of these ancient events, preserved in the arrangement of galaxies across billions of light years. Let us also consider the role of magnetic fields in cosmic structure. Galaxies and galaxy clusters are permeated by magnetic fields, detected through their effects on cosmic rays and polarized radiation. The origin of these magnetic fields is not fully understood. They might have been generated by processes within galaxies, or they might be primordial, created in the early universe and amplified over time. Primordial magnetic fields could have interesting effects on large-scale structure. Magnetic pressure can resist gravitational collapse in some directions while allowing it in others, creating anisotropic structure that differs from pure gravitational predictions. If primordial magnetic fields had coherent orientation over large scales, they could have seeded the formation of elongated structures like walls and filaments. The giant arc, with its distinctive curved shape, might be particularly relevant here. Curved structures are unusual in gravitational dynamics, which tends to produce linear filaments and sheet-like walls. A magnetic field with curved geometry could potentially seed a curved structure, though the details would need to be worked out. Magnetic fields also interact with cosmic rays, high-energy particles that permeate intergalactic space. Cosmic rays are deflected by magnetic fields, causing them to trace out the field lines rather than traveling in straight paths. By studying the distribution of cosmic rays, astronomers can in principle map the large-scale magnetic field structure of the universe. Future observations with instruments like the Pierre Auger Observatory and the Telescope Array might reveal whether cosmic rays are deflected in patterns consistent with giant magnetic structures. This would provide independent evidence for large-scale coherence in the universe, complementing the observations of galaxy distributions. Now let us consider what the giant structures tell us about the ultimate fate of the universe. In the standard model, dark energy will cause the expansion of the universe to accelerate forever. Galaxy clusters will drift apart, eventually losing sight of each other as they pass beyond each other's cosmic horizons. Stars will burn out, black holes will evaporate, and the universe will fade into cold, dark emptiness. But the giant structures complicate this picture. If they are gravitationally bound, they represent concentrations of matter that might resist the accelerating expansion longer than isolated galaxy clusters. The internal gravity of a 10 billion light-year structure would be enormous, potentially capable of holding the structure together even as the surrounding space stretches apart. Of course, for a structure to resist dark energy, its internal gravity must exceed the outward pull of the expanding space. This is a question of density. Denser structures can hold together, while less dense structures get torn apart. We do not know the exact density of the giant structures, as much of their mass is dark matter that we can detect only indirectly. If the giant structures are dense enough to remain bound, they could survive far longer than isolated galaxies and clusters. They would be cosmic islands of stability in an increasingly empty universe, refuges where matter and perhaps Life could persist long after the rest of the cosmos has darkened. This is a speculative scenario, but it raises fascinating questions about the long-term future. If giant bound structures exist, they could fundamentally change the habitability of the far future universe. Rather than isolated systems drifting apart in infinite loneliness, there could be vast interconnected regions where matter continues to interact and evolve. On the other hand, if the giant structures are not actually gravitationally bound, if they are more like temporary alignments than permanent configurations, then their fate would be different. The accelerating expansion would eventually tear them apart, scattering their component galaxies across unimaginable distances. In this scenario, the giant structures are transient phenomena, impressive now, but destined to dissolve into the cosmic background. Determining which scenario is correct requires better understanding of the structure's internal dynamics. We need to measure not just where the galaxies are located, but how they are moving. If the galaxies within a giant structure are falling toward each other, the structure is collapsing under its own gravity and will become more tightly bound over time. If they are moving apart faster than the overall cosmic expansion, the structure is dissipating and will eventually cease to exist as a coherent entity. Such measurements are extremely challenging. The distances are enormous, the motions are tiny compared to the overall expansion, and separating peculiar velocities from the Hubble flow requires precise observations over long baselines. But advances in technology are making such measurements increasingly feasible. Future surveys may tell us whether the giant structures are permanent residents of the cosmic landscape or temporary visitors passing through. Let us now explore the aesthetic and emotional dimensions of contemplating these cosmic structures. Science is often presented as a purely rational enterprise, but scientists are humans who experience wonder, awe, and sometimes fear when confronting the unknown. The giant structures evoke all of these emotions in those who study them. There is wonder at the sheer scale of what we have discovered. A structure spanning 10 billion light-years defies imagination. No metaphor adequately captures what it means for something to be that large. We can say it is bigger than 1 billion Milky Ways, but what does that really mean to a brain that evolved to understand distances measured in footsteps and arm lengths? There is awe at the intricate beauty of the cosmic web. The patterns of filaments and nodes are not random, but follow elegant mathematical relationships, the signature of physical laws operating across cosmic time. The universe has structured itself according to principles we can partially understand, creating a tapestry of matter that is both chaotic and ordered. There is also a kind of fear, or at least unease, at confronting something that defies our understanding. Scientists like to explain things. We like to fit observations into theoretical frameworks that make sense of the data. When observations stubbornly refuse to fit, when they challenge our deepest assumptions about how the universe works, there is a discomfort that motivates further investigation. The giant structures produce all of these responses. They are wonderful in the original sense of the word, full of wonder. They are awe-inspiring in their scale and complexity, and they are unsettling in their challenge to our models, their stubborn refusal to conform to theoretical predictions. Perhaps this emotional engagement is part of what makes cosmology such a compelling field. We are not just solving abstract problems or collecting data for its own sake. We are exploring the most fundamental questions about reality, questions that touch on our place in the universe and the nature of existence itself. The emotional stakes are high because the intellectual stakes are high. Let us consider how future discoveries might change our perspective on the giant structures. Science is always provisional, always subject to revision in light of new evidence. What seems impossible today might be routine tomorrow, explained by theories we have not yet imagined. One possibility is that the giant structures will be explained within the existing framework through some combination of measurement corrections and theoretical refinements. Perhaps the structures are somewhat smaller than current estimates suggest, and perhaps our models can be adjusted to accommodate slightly larger structures without fundamental revision. In this scenario, the giant structures become interesting extreme examples rather than revolutionary discoveries. Another possibility is that the giant structures will force a paradigm shift, a fundamental rethinking of how we understand cosmic evolution. This would be the more exciting outcome scientifically, though also the more challenging. Paradigm shifts require abandoning cherished ideas and building new frameworks from scratch, a process that can take decades and involves much controversy along the way. History provides precedents for both outcomes. Some anomalies that seemed revolutionary at first were eventually explained within existing frameworks. The initial apparent discrepancy between predicted and observed perihelion precession of Mercury was resolved by refinements to orbital calculations long before general relativity provided a deeper explanation. Other anomalies proved genuinely revolutionary, like the perihelion precession that remained after refinements, which eventually required Einstein's new theory of gravity. Which category will the giant structures fall into? We do not know yet. The evidence is still being gathered, the models are still being developed, and the scientific consensus is still forming. What we can say is that the question is being taken seriously by the scientific community, with researchers around the world working to understand what these impossible structures mean for our picture of the cosmos. The process of scientific investigation is itself beautiful, a collaborative human endeavor to understand the universe we inhabit. Thousands of astronomers operating telescopes, analyzing data, developing theories, debating interpretations, all working together across national boundaries and cultural differences toward the common goal of knowledge. Whatever the ultimate explanation for the giant structures, the process of finding that explanation is a testament to human curiosity and cooperation. Let us now describe some of the individual galaxies and clusters that make up these giant structures. While we have focused on the large-scale patterns, the structures are ultimately composed of countless individual objects, each with its own story. Consider the galaxies in the Hercules-Corona Borealis Great Wall. There are likely billions of them, ranging from giant ellipticals larger than the Milky Way to tiny dwarf galaxies containing just a few million stars. Each galaxy has its own collection of planets and potentially its own forms of life. The wall is not just a statistical pattern, but a vast assemblage of unique individual systems. The giant elliptical galaxies in this wall probably contain some of the most massive black holes in the universe, monsters weighing billions of solar masses that dominate the cores of their host galaxies. These black holes grow by consuming gas and smaller galaxies, their gravitational pull drawing material inward in swirling accretion disks that can outshine entire galaxies. The wall also contains galaxy clusters, concentrations of hundreds or thousands of galaxies bound together by gravity. These clusters are the largest gravitationally bound objects in the universe, at least within the Standard Model framework. They are immersed in vast halos of hot gas, heated to millions of degrees by the violence of gravitational collapse. This gas emits X-rays that can be detected from Earth, providing another way to map the distribution of matter in the distant universe. Between the clusters lie the filaments, chains of galaxies connecting the dense nodes. these filaments are the highways of the cosmic web, channels along which matter flows toward the clusters. Galaxies traveling along filaments are subject to various environmental effects that can transform their properties over time. The diversity within the giant structures is as remarkable as their overall scale. No two galaxies are identical. No two clusters have exactly the same composition. The structures are not uniform walls, but textured assemblages with internal complexity at every level. Understanding this complexity is part of understanding the structures themselves. Some researchers have wondered whether the giant structures might affect the galaxies within them in unique ways. Does living in a 10 billion light-year wall influence a galaxy's evolution differently than living in a more typical region of the cosmic web? This is difficult to test because we have only one example of such a structure to study, and isolating its effects from other factors is challenging. But as surveys improve and more giant structures are potentially discovered, comparative studies may become possible. If galaxies in giant structures have systematic differences from galaxies elsewhere, those differences could provide clues about the formation and nature of the structures themselves. Let us delve deeper into the relationship between these cosmic structures and the fundamental nature of space and time. In general relativity, space and time are not fixed backgrounds, but dynamic entities that respond to matter and energy. Massive objects curve space around them, and this curvature is what we experience as gravity. On the scale of planets and stars, this curvature is subtle but measurable. Light passing near the Sun is bent by a tiny angle, enough to shift the apparent positions of stars during solar eclipses. Clocks on GPS satellites run slightly faster than clocks on Earth's surface because they experience less gravitational time dilation. But on the scale of giant cosmic structures, the curvature could be significant. A wall of galaxies spanning billions of light-years would contain an enormous amount of mass, creating gravitational distortions that extend across vast regions of space. Light passing through such a structure would be bent and delayed. Time would run differently in different parts of the structure, and the very geometry of space would be warped by the presence of so much matter. These effects are difficult to detect directly because we have no way to compare conditions inside and outside the structure. We are immersed in our local cosmic environment with no external reference point, but subtle signatures might reveal the presence of these geometric distortions. One such signature involves the way distant objects appear to us. If space is curved by a giant structure along our line of sight, objects behind the structure might appear distorted or displaced from their true positions. This is essentially gravitational lensing on a grand scale, not the strong lensing that creates multiple images of distant quasars, but a weak, systematic distortion that affects the apparent shapes and positions of many background objects. Astronomers have searched for such signatures in the distribution of distant galaxies, looking for coherent patterns that might indicate the presence of intervening mass concentrations. The results have been intriguing, but not conclusive. There are hints of large-scale correlations that could be caused by giant structures, but the signal is weak and difficult to separate from other effects. Another signature involves the cosmic microwave background, the ancient light that provides our earliest view of the universe. As this light travels toward us, it passes through the cosmic web, gaining or losing energy depending on the gravitational landscape it traverses. This effect, known as the integrated Sachs-Wolf effect, creates subtle temperature variations in the microwave background that correlate with the distribution of large-scale structure. The integrated Sachs-Wolf effect has been detected and measured, confirming that large-scale structures do leave imprints on the cosmic microwave background. But the effect depends on dark energy and the cosmological model, making it a test of both structure and theory simultaneously. If the giant structures are associated with unusual dark energy conditions, the integrated Sachs-Wolf effect might show anomalies in those regions. Researchers continue to develop new methods for studying the geometric effects of giant structures. As our understanding of gravitational physics improves and our observational capabilities expand, we may eventually be able to map the curvature of space created by these enormous concentrations of matter. Now, let us consider what it would be like to travel across one of these giant structures. Of course, such a journey is impossible with any technology we can currently imagine. Even at the speed of light, crossing the Hercules-Corona Great Wall would take 10 billion years, longer than the current age of the universe. No spacecraft, no beam of light, no signal of any kind could make this journey in any humanly meaningful timescale. But let us imagine anyway. Suppose you could somehow travel across this vast wall, experiencing its full extent. What would you encounter along the way? You would start in a galaxy much like our own, a spiral of hundreds of billions of stars orbiting a central bulge. Looking out from your starting point, you would see other galaxies in every direction, some nearby and some far away, their light providing beacons in the cosmic darkness. As you traveled, you would pass through the intergalactic medium, the sparse gas that fills the space between galaxies. This gas is incredibly thin by earthly standards, with only about 1 atom per cubic meter, compared to the billion trillion atoms in each cubic meter of air you breathe. Yet across cosmic distances, even this thin gas adds up, containing more mass than all the visible stars combined. You would encounter galaxy clusters, vast assemblages of hundreds or thousands of galaxies held together by their mutual gravity. Entering a cluster, you would pass through the intracluster medium, gas heated to millions of degrees by the violence of gravitational collapse. This gas glows in X-rays, creating a diffuse glow that fills the space between cluster members. You would traverse the filaments of the cosmic web, chains of galaxies connecting the clusters like strands of a spider web. Along these filaments, matter flows toward the nodes, drawn by gravity across millions of light years. Galaxies in the filaments are being transformed by their journey, their gas stripped away, their star formation quenched, their fates determined by their position in the cosmic web. And through it all, you would be immersed in the dark matter that dominates the mass of these structures. Invisible and undetectable except through its gravitational effects, dark matter provides the scaffolding on which visible matter is arranged. You would pass through dark matter halos surrounding every galaxy and cluster, through the dark filaments connecting them, through the vast, dark background that fills the cosmos. After billions of years of travel, you would still be within the same giant structure. You would have passed through countless galaxies, traversed countless filaments, encountered countless clusters, and yet you would not have reached the edge. The structure extends further than you have traveled, further than you can imagine traveling, a wall of matter stretching across 1/10 of the observable universe. This mental journey helps to convey the true scale of what we are discussing. The giant structures are not just large by human standards, or even by astronomical standards. They are large by the standards of the universe itself, spanning significant fractions of everything that exists. Let us now explore the history of how our understanding of cosmic structure has evolved. The story begins before we knew the true scale of the universe, when astronomers were just beginning to comprehend that the fuzzy patches they saw in the night sky were not local nebulae, but distant collections of billions of stars. In the early 20th century, the great debate raged about the nature of spiral nebulae. Were they small objects within our Milky Way, or were they island universes in their own right, vast collections of stars separated from us by unimaginable distances? The debate was resolved in the 1920s when Edwin Hubble measured the distances to nearby galaxies using Cepheid variable stars, proving that the universe extended far beyond the confines of our own galaxy. Hubble's discovery opened the door to extragalactic astronomy, the study of the universe beyond the Milky Way. As telescopes improved and surveys expanded, astronomers began to map the distribution of galaxies across ever larger volumes of space. Early maps were sparse and limited, showing only the brightest and nearest galaxies. But even these early maps hinted at structure, at clustering and patterns that suggested the galaxies were not distributed randomly. By the 1970s, surveys had become comprehensive enough to reveal the first outlines of the cosmic web. Astronomers noticed that galaxies tended to concentrate in certain regions while avoiding others. The voids and filaments began to emerge from the data, suggesting that the universe had organized itself into a vast, interconnected network. The discovery of the Great Wall in 1989 marked a new era in our understanding of large-scale structure. Here was a coherent structure stretching across hundreds of millions of light-years, far larger than anything previously known. The Great Wall demonstrated that structure formation continued to scales beyond what many had expected, challenging theorists to explain how such large features could arise. The following decades brought increasingly detailed maps of the cosmic web. The Sloan Digital Sky Survey, beginning in 2000, catalogued millions of galaxies with unprecedented precision. The 2-degree field galaxy redshift survey, the 2-micron all-sky survey, and numerous other projects contributed to a growing 3-dimensional atlas of the nearby universe. These surveys revealed structure at every scale they could probe. Galaxy groups and clusters gave way to superclusters and walls, which in turn were connected by filaments stretching across hundreds of millions of light-years. The cosmic web emerged in ever finer detail, a tapestry of matter woven across cosmic space. But the surveys also revealed something troubling. As the mapped volume grew, so did the size of the largest structures detected. The Sloan Great Wall exceeded 1 billion light-years. Other structures approached or exceeded the theoretical maximum. And then came the discoveries of truly giant structures, walls and arcs that shattered all expectations. The history of cosmic cartography is thus a history of expanding horizons and receding limits. Every time we thought we understood the maximum scale of structure, we discovered something larger. Every time we thought we had mapped the full extent of the cosmic web, we found that it extended further than we realized. This pattern raises a troubling question. Have we reached the true limit yet? Or will future surveys reveal structures larger still? The observable universe has a finite size, about 93 billion light-years in diameter. We cannot see beyond this horizon because light from more distant regions has not had time to reach us. But within this volume, is there a maximum scale for structure? Or does structure continue to larger and larger scales all the way to the cosmic horizon? The standard model says there should be a maximum scale set by the physics of structure formation. But the observations seem to disagree. Either the maximum is higher than we thought, or there is no maximum at all. Both possibilities are troubling in different ways. If the maximum is simply higher than predicted, we need to modify our models, but not abandon them entirely. This is the more conservative interpretation, requiring tweaks rather than revolutionary changes. But even tweaks can have far-reaching implications when they involve the fundamental assumptions underlying cosmology. If there is no maximum at all, if structure continues to arbitrary scales, then the cosmological principle might be fundamentally wrong. The universe might not be homogeneous even on the larger scales. It might have a grain or texture that persists to the very edge of the observable volume. This would require a much more radical revision of our cosmic worldview. The coming years will help to clarify which interpretation is correct. New surveys will probe larger volumes at higher precision, revealing whether the giant structures are exceptional outliers or representative of ongoing patterns. New theoretical work will explore modifications to the standard model, seeking frameworks that can accommodate giant structures while preserving the many successes of Lambda-CDM. Let us now consider the role of chance and probability in the formation of cosmic structure. The universe we see today emerged from tiny quantum fluctuations in the early cosmos, random variations in density that were later amplified by gravity. In this sense, the specific arrangement of galaxies and structures we observe is contingent, one realization out of countless possibilities. If we could rerun the universe with slightly different initial conditions, the detailed pattern of the cosmic web would be different. Different galaxies would form in different locations. Different structures would emerge at different scales. The statistical properties might be similar, but the specific arrangement would be unique. This raises interesting questions about the giant structures. Are they typical outcomes of cosmic evolution? Things we should expect to find in any realization of a universe like ours? Or are they statistical flukes, unlikely arrangements that happen to occur in our particular cosmic history? If the giant structures are typical, then our models need significant revision. Kwok Kim, T. Min. They fail to predict something that should be common. The physics of structure formation must be different from what we assumed. If the giant structures are flukes, then our models might still be approximately correct. We might just be observing a rare tale of the distribution, an improbable but not impossible outcome. In a universe containing billions of galaxies across billions of light years, rare events will sometimes occur. Distinguishing between these possibilities requires careful statistical analysis. We need to calculate how likely structures like the Hercules-Corona Borealis Great Wall are to occur by chance, given the volume of space we have surveyed and the inherent randomness of structure formation. The calculations have been done, and they suggest that the giant structures are indeed improbable within the standard model. The Hercules-Corona Borealis Great Wall has less than a 1 in 10,000 chance of arising from standard fluctuations in a Lambda-CDM universe. This does not mean it is impossible, but it does mean that finding such a structure should prompt us to question our assumptions. One response to this improbability is to invoke the anthropic principle, the idea that we necessarily observe a universe compatible with our existence. Perhaps giant structures are rare, but perhaps observers can only exist in universes where such structures form. This would explain why we see them, not because they are common, but because our existence is somehow tied to their presence. This anthropic argument is controversial and not very satisfying. It is hard to see how giant structures billions of light years away could influence whether intelligent life evolves on a small rocky planet. The connection seems too remote to be compelling. A more productive response is to take the improbability seriously as evidence that our models need revision. The giant structures are telling us something important about the universe, something that our current theories fail to capture. Listening to what they say requires being open to new possibilities. Before we conclude entirely, let us take one more excursion into the depths of cosmic structure. There are aspects of this story we have touched on only briefly that deserve deeper exploration, threads that weave through everything we have discussed and connect these giant structures to the fundamental nature of existence. Consider the relationship between space and the matter it contains. In our everyday experience, space seems passive, a stage on which the drama of physics plays out. Objects move through space, forces act across space, time flows through space. But general relativity reveals that space is far more than a passive backdrop. Space itself is a physical entity, shaped by matter and in turn shaping how matter moves and evolves. The giant cosmic structures are not merely arrangements of galaxies within space. They are regions where space itself is curved and distorted by the enormous concentrations of mass. The geometry of space varies across these structures, with different regions experiencing different amounts of curvature depending on the local density of matter. This intimate connection between matter and geometry has profound implications. When we say that a structure spans 10 billion light-years, we are making a statement about geometry as much as about matter. The distance itself is defined by the curvature of space, which is influenced by the matter distribution we are trying to measure. In some sense, the giant structures are measuring themselves, their own gravity affecting the very metric by which we characterize their size. This circularity does not mean our measurements are meaningless. Cosmologists have developed sophisticated techniques to account for the interplay between matter and geometry. But it does remind us that the cosmic web is not separate from space-time. The structures are features of space-time, not merely objects within it. The same principle applies to time. Clocks within the giant structures tick at slightly different rates than clocks in emptier regions, a consequence of gravitational time dilation. The densest parts of the structures experience time differently than the sparse voids between them. The history of the cosmos is not uniform but textured, with different regions aging at slightly different rates depending on their gravitational environment. These effects are tiny, by human standards, amounting to fractions of a percent over billions of years. But over cosmic timescales, even small differences accumulate. The giant structures have had more or less time to evolve, depending on where within them you look, creating subtle variations in the properties of their constituent galaxies. Some researchers have wondered whether these gravitational time effects might influence the apparent sizes of the structures. If our distance measurements are sensitive to time as well as space, then structures embedded in regions of different gravitational potential might appear larger or smaller than their true sizes. This is unlikely to explain the full magnitude of the anomaly, but it adds another layer of complexity to an already subtle problem. Let us also consider the role of quantum mechanics in these cosmic structures. At first glance, quantum mechanics and cosmology seem to operate on entirely different scales. Quantum effects are typically important for subatomic particles, while cosmology deals with the largest scales imaginable. But the connection between them is deeper than it might appear. The seeds of all cosmic structure were quantum fluctuations, random variations in the density of the early universe caused by the inherent uncertainty of quantum physics. These fluctuations were microscopic when they formed, smaller than atoms, existing only as probability distributions in quantum fields. But cosmic inflations stretch them to astronomical scales, transforming quantum fuzz into the initial conditions for galaxy formation. In this sense, the giant cosmic structures are quantum effects writ large. The pattern of walls and filaments and voids that we see today is the amplified shadow of quantum uncertainty from the first fraction of a second after the Big Bang. The Hercules-Corona Great Wall, spanning 10 billion light-years, traces its origin back to quantum fluctuations no larger than the nucleus of an atom. This connection between the smallest and largest scales is one of the most beautiful aspects of modern cosmology. The entire cosmic web, including the impossible giant structures, emerged from quantum physics operating in the unimaginable conditions of the newborn universe. Understanding the cosmic web is thus intimately tied to understanding quantum mechanics and the physics of the early cosmos. Some researchers have speculated that the giant structures might provide clues about quantum gravity, the sought-after theory that would unify quantum mechanics with general relativity. Quantum gravity effects are normally expected to be important only at incredibly small scales, the Planck length of about 10 to the minus 33 centimeters. But inflation could have stretched quantum gravity effects to observable scales, just as it stretched ordinary quantum fluctuations. If the giant structures show unusual properties that cannot be explained by standard physics, this might be a hint that quantum gravity effects have left their mark on the cosmic web. The structures would then be fossils of the earliest moments of cosmic history, windows into physics that we cannot probe in any other way. This is highly speculative, and no clear evidence for quantum gravity in large-scale structure has yet emerged. But it illustrates how the study of giant cosmic structures connects to the most fundamental questions in physics. These are not isolated anomalies, but potential clues to the deepest nature of reality. Let us also reflect on the meaning of discovery itself. When we say that we have discovered the giant cosmic structures, what exactly have we done? We have not created them. We have not traveled to them. We have not touched them or interacted with them in any direct way. We have merely gathered light and other radiation that traveled billions of years to reach our instruments, interpreted that information using mathematical models, and formed mental representations of structures too vast to visualize. Yet this process of discovery is genuine and profound. Before our observations, the giant structures existed but were unknown to any mind in our cosmic neighborhood. Through careful work over many decades, we have brought them into the realm of human knowledge. They are now part of our understanding of the universe, entities that we can name and describe and reason about. Discovery is a form of creation, not of the physical reality itself, but of its representation in conscious experience. The giant structures were always there, but their existence in human understanding is new. We have added something to the universe by recognizing what was already present, by transforming raw signals into meaningful knowledge. This process continues. Right now, as you listen to these words, astronomers around the world are gathering new data, analyzing new observations, developing new theories. The story of cosmic structure is not finished but ongoing, with new chapters being written every day. What we know today is more than we knew yesterday, but less than we will know tomorrow. The giant structures have taught us humility. They have shown us that even our most successful theories have limits, that the universe contains surprises we never anticipated. But they have also taught us confidence. Despite the challenges, despite the anomalies, despite the failures of our predictions, we continue to learn. The scientific method works. Patient observation combined with careful reasoning gradually reveals the truth. We stand at a fascinating moment in the history of cosmology. The old certainties have been shaken by discoveries that defy explanation. The new frameworks have not yet crystallized. We are between paradigms, in a state of productive uncertainty that may well lead to revolutionary advances. The giant cosmic structures are signposts pointing toward that future. They tell us that we do not yet understand the universe as well as we thought. They challenge us to think more deeply, observe more carefully, theorize more boldly. They are problems waiting to be solved, mysteries waiting to be unraveled. What will we discover next? What new structures might emerge from future surveys? What theoretical breakthroughs might explain what we have already found? These questions animate the cosmological community and drive the endless pursuit of knowledge. The universe does not give up its secrets easily. It requires patience and persistence, imagination and rigor, the combined efforts of thousands of researchers over many generations. But the rewards are worth the effort. Each discovery expands our understanding, pushes back the boundaries of the unknown, and brings us closer to comprehending the cosmos that gave us birth. The structure so large it broke our understanding of space is a reminder of how much we have yet to learn. It is also a promise of how much we will eventually discover. The universe is vast and strange and beautiful, filled with wonders we have not yet imagined. Our task is to keep exploring, keep asking, keep wondering. And so the story continues, as it always has and always will, as long as there are minds to contemplate the cosmos and hearts to wonder at its majesty. We have journeyed far together, from the familiar confines of Earth out to the most distant reaches of the observable universe. We have encountered structures so vast that they challenge our understanding of reality, walls and arcs and rings of galaxies stretching across billions of light years. We have explored the physics of how they might have formed and the implications of their existence for our cosmic worldview. Now let us bring our journey to its culmination, confronting the deepest mysteries that these giant structures reveal. The central question is simple to state but profound in its implications. Why does the universe contain structures that should not exist? Our best theories, refined over decades and tested against countless observations, say that structures larger than about 1.2 billion light-years cannot form. The physics does not allow it. There has not been enough time since the Big Bang for gravity to assemble anything larger. Yet the evidence before us is unmistakable. The Hercules-Corona Great Wall spans 10 billion light-years, more than 8 times the theoretical maximum. The giant arc stretches 3.3 billion light-years, nearly 3 times the limit. The Big Ring, the Sloan Great Wall, and other structures push against or exceed the boundaries of what should be possible. Something is wrong with our understanding. Either our observations are mistaken, our models are incomplete, or our fundamental assumptions about the universe are flawed. The first possibility seems increasingly unlikely as multiple independent teams using different methods continue to confirm the existence of these structures. The second and third possibilities are more troubling, but also more exciting, because they point toward new physics waiting to be discovered. Let us consider the most radical possibility, that the cosmological principle itself is wrong. This principle, which states that the universe is homogeneous and isotropic on large scales, is one of the foundational assumptions of modern cosmology. It is built into our equations, implicit in our interpretations, fundamental to our understanding of cosmic evolution. If the cosmological principle fails, then the universe has structure all the way up. There is no scale at which things average out to uniformity. The cosmic web continues to larger and larger patterns, with walls and filaments and voids extending to the very edge of the observable universe and presumably beyond. This would be a revolutionary discovery, forcing a complete rethinking of how we understand the cosmos. Our equations would need to be rewritten. Our interpretations would need to be revised. Our picture of cosmic evolution would need to be fundamentally altered. But revolution in science is not unprecedented. The history of physics is punctuated by moments when old assumptions were overturned and new frameworks emerged. The Copernican revolution displaced Earth from the center of the universe. The relativistic revolution changed our understanding of space and time. The quantum revolution transformed our picture of matter and energy. Perhaps we are on the cusp of another such revolution, one in which the cosmological principle is abandoned and replaced by a new understanding of large-scale structure. The giant structures would be the evidence that drove this revolution, the anomalies that demanded explanation and ultimately led to deeper truth. Or perhaps the resolution will be more modest. Perhaps our models can be tweaked to accommodate larger structures without abandoning the cosmological principle entirely. Perhaps the structures are extreme statistical outliers, rare but not impossible. Perhaps there are processes we have overlooked that can enhance structure formation beyond standard predictions. The honest answer is that we do not know. The mystery remains unsolved. The giant structures hang over cosmology like a challenge, demanding attention and resisting easy explanation. But this uncertainty is not a failure of science. It is science working as intended. Science advances by confronting puzzles, not by ignoring them. The giant structures are puzzles of the highest order, and their eventual solution will teach us something profound about the nature of reality. Let us step back now and appreciate the magnitude of what we have learned. 100 years ago, we did not know that galaxies existed beyond our own. 50 years ago, we did not know about the cosmic web. 20 years ago, we did not know about giant structures that defy our theories. Each generation of astronomers has discovered that the universe is larger, more complex, and more mysterious than the generation before imagined. This pattern suggests that our current understanding, as detailed and successful as it is, remains incomplete. There are surely phenomena out there that we have not yet detected, structures that we have not yet mapped, physics that we have not yet discovered. The universe is under no obligation to be comprehensible, and yet comprehension is precisely what we seek. The giant structures remind us of our limitations, but they also inspire us to transcend them. Every puzzle is an opportunity. Every mystery is a door waiting to be opened. The history of science shows that nature eventually yields its secrets to those who ask the right questions and pursue the answers with persistence and creativity. What questions should we be asking about the giant structures? Here are a few that keep cosmologists awake at night. Are there even larger structures waiting to be discovered? Our surveys have covered only a fraction of the observable universe in sufficient detail to detect such features. As surveys expand and improve, will we find walls and arcs that make the current giants seem modest? What is the internal structure of these features? We see them from a distance, as patterns in the distribution of galaxies and gamma-ray bursts. But what is happening inside them? How are galaxies forming and evolving within these enormous environments? How do the giant structures relate to dark matter and dark energy? These mysterious components dominate the universe, but remain poorly understood. Could the giant structures provide new clues about their nature? Is the universe truly homogeneous on any scale? Or does structure continue indefinitely, with patterns at every level from atoms to the cosmic horizon? These questions may take decades to answer. They may require technologies we have not yet invented and theories we have not yet formulated, but they will be answered eventually, as long as human curiosity persists and the scientific enterprise continues. Now, let us return to where we began, to the simple, profound fact that captured our attention at the start of this journey. The structure so large it broke our understanding of space. This is not hyperbole. It is an accurate description of what we have discovered. Our understanding of space, encoded in the equations of general relativity and the standard cosmological model, does not allow for structures this large. Yet they exist. The universe has shown us something that our theories say should be impossible. In some ways, this is the most exciting situation in science. When observations and theory disagree, when the universe refuses to conform to our expectations, that is when breakthroughs happen. The discrepancy between Mercury's orbit and Newtonian predictions led to general relativity. The discrepancy between black-body radiation and classical physics led to quantum mechanics. The discrepancy between galaxy rotation curves and visible matter led to the discovery of dark matter. What breakthrough might the giant structures lead to? We cannot say yet, but we can be confident that pursuing this mystery will teach us something important. Nature is speaking to us through these enormous features. Our job is to listen and to understand. The universe is stranger than we thought. It contains structures that span significant fractions of the observable volume, walls and arcs and rings of galaxies that stretch across billions of light years. These structures challenge our deepest assumptions about cosmic evolution and point toward new physics waiting to be discovered. But perhaps the most remarkable thing about these structures is not their size, but the fact that we discovered them at all. Tiny creatures on a small planet orbiting an ordinary star in a typical galaxy have mapped the cosmos across billions of light years. We have found patterns and structures that dwarf everything in our experience. We have confronted mysteries that push the boundaries of human comprehension. This is the triumph of science, that finite beings can contemplate the infinite, that small minds can grapple with vast realities, that a species barely emerged from caves can chart the architecture of the universe. The giant structures are humbling, yes. They remind us how small we are in the cosmic scheme, but they are also inspiring. They show us what we are capable of discovering when we look up at the night sky with curiosity and wonder. What else is out there waiting to be found? What other mysteries lurk in the cosmic darkness? What other surprises does the universe have in store? We do not know, and that is precisely what makes science so exciting. The journey of discovery continues, one observation at a time, one theory at a time, one insight at a time. The structure so large it broke our understanding of space is not an ending, but a beginning. It is an invitation to explore further, to think deeper, to question more boldly. The universe has shown us that our current understanding is incomplete. Now it is up to us to build something better. As you drift towards sleep tonight, perhaps the image of these cosmic structures will stay with you. Perhaps you will dream of walls of galaxies stretching across the void, of arcs and rings traced out in starlight, of a universe vaster and stranger than anything you imagined. And perhaps, when you wake, you will carry with you a renewed sense of wonder at the cosmos we inhabit. The universe is large beyond measure. It is ancient beyond comprehension. It is complex beyond our current understanding. And it is beautiful beyond words. We are here, on this small planet, in this small moment of cosmic time, looking out at the immensity of creation. We have discovered structures that span billions of light years. patterns in the fabric of space that challenge everything we thought we knew. We have found evidence that the universe is even stranger, even more magnificent, even more mysterious than our theories predicted. This is the gift that cosmology offers, a window onto the infinite, a glimpse of the cosmic architecture that surrounds us. The giant structures are just one chapter in a story that has been unfolding for 13.8 billion years and will continue for billions more. We are privileged to be the creatures who discovered them, the minds who contemplated them, the curious souls who asked why they exist. The question remains unanswered. The mystery persists. But that is as it should be. The universe does not owe us easy answers. It offers only clues, hints, fragments of a truth that may take generations to fully comprehend. And so, we continue to look up, to observe, to wonder, to theorize. We build telescopes and satellites. We develop equations and simulations. We ask questions that would have seemed absurd to our ancestors and pursue answers that may seem incomplete to our descendants. This is the human enterprise at its finest. The endless quest to understand our place in the cosmos. The giant structures are milestones on that quest, markers of how far we have come and how far we still have to go. Sleep well tonight, knowing that you live in a universe of wonders. Dream of structures stretching across billions of light years, and wake tomorrow ready to ask new questions about the cosmos that gave you birth. The journey continues, the mystery deepens, the wonder grows, and that, in the end, is all we can ask from a universe this vast, this ancient, this magnificently strange. If you enjoyed this journey through the cosmos, please consider subscribing to this channel and leaving a like. Your support allows us to keep exploring the strangest and most wonderful mysteries of our universe together. Until next time, keep looking up at the stars and never stop wondering what lies beyond.